Okay, Bismillah ar-Rahman ar-Rahim. Today is lecture number 4 of the course Irrigation Engineering. In today's lecture, we will continue our discussion about the crop water requirements and its measurement. And towards the end of the lecture, we will discuss about the quality of irrigation water. Now, we discuss the soil moisture irrigation relationship. You can see that we supply the water to the crops that can come in the form of either natural rainfall or artificial application of water. When this water is supplied, so some of the water appears as surface runoff, while the other portion infiltrates into the soil, and in the root zone this water is taken up by the roots of the plants and is used in the evapotranspiration process. There will be also percolation of this infiltrated water that will act as a recharge to the groundwater. Now, the water below the water table is known as groundwater, and above the water table is soil moisture. So we have this water table. This is the upper zone or upper limit of the saturation zone. Above this water table, we have soil moisture. And below this water table, the pores of the soil that is completely filled with water, that is fully saturated, so that is known as the groundwater. Below the ground surface is the soil zone or root zone that is penetrated by the roots of vegetation. So you can see that below the surface we have what is known as the soil zone or root zone that is penetrated by the roots of vegetation, plants, crops. Root zone is the most important from irrigation point of view because the plants take their water supply from this zone. When water falls over the ground, a part of it get absorbed in the root zone and the rest flows down under the action of gravity. So when water falls over the surface, either artificial application in the form of irrigation or natural rainfall, so the water that infiltrates into the soil, so a part of it get absorbed in the root zone, and some of the water, the rest of the water will flow downward under the action of gravity to join the groundwater. So we defined some important concepts now. First one is the field capacity. So after the rain or irrigation is stopped, part of water held in the larger pores of soil moves downward, called percolation or drainage. So the water infiltrates the entrance of the water into the soil, that is infiltration. And then the downward movement through the soil profile, so that is known as percolation. As the drainage stops, the large soil pores are filled with both air and water, whereas the small pores are still full of water. The soil at this stage is said to be at field capacity. So what is field capacity? The field capacity is the amount of maximum moisture that can be held by the soil against gravity. It is generally expressed as percentage. So what is the field capacity? It is the amount of maximum moisture that can be held by the soil against gravity. Now when water is supplied, so the soil that becomes fully saturated, then due to the gravity some water will drain. Due to percolation it will go down, but some of the water that will be held by the soil against the gravity. So the amount of maximum moisture that can be held by the soil against gravity, that is known as field capacity. Or the field capacity is the moisture content of the soil after free drainage has removed most of the gravity water. So it is that moisture content of the soil after free drainage, that is due to the gravity, has removed most of the gravity water. Now what is the use of this concept of field capacity? So the concept of field capacity is useful in arriving at the amount of water available in the soil for plant use. So this concept is very important. It is useful in arriving at the amount of water that is available in the soil that can be taken up by the plants for meeting their evapotranspiration needs. The field capacity is thus the water content of a soil after free drainage has taken place for a sufficient period. Now, how much time is taken by this free drainage? So the period of free gravity drainage is usually taken as 2 to 5 days, depending on the different conditions, soil conditions. So it ranges between 2 to 5 days. So field capacity, that can be mathematically written as weight of water retained in certain volume of soil divided by the weight of the same volume of dry soil, and it is expressed as percentage. So it is actually the water content is field capacity. So you can see here soil moisture conditions. When the water is supplied to the soil, you can see here that when it is fully saturated, then some of the water that will percolate downward due to the effect of gravity. So this is known as the gravity water. Now after this gravity water is drained, then the water that is held by the soil pores against the gravity, or that is known as the field capacity. That is known as the field capacity. Now typically what is the situation is that when we have the pores of the soil, so you can see that it is partially filled with water and partially filled with air, because it cannot be fully saturated. In the groundwater, the pores are completely filled with water, but in the unsaturated zone, so the pores will be partially filled with water and partially filled with air. So this is the typical. This is what you can see here also. Now the wilting point that we will define, so it is that moisture which cannot be extracted by the plants to meet their evapotranspiration needs. So it means that this is actually the water that is available the soil moisture that is available to the plants, that varies between the field capacity and the wilting point. Now, soil water availability and classes. So we have the gravitational water. It is the water in the large pores that moves downward freely under the influence of gravity. It drains out so fast that it is not available to the crops. You can see here that when the soil is completely saturated due to the natural rainfall, or we artificially supply the water to the crops, so in this case you see that some of the water, it will be drained due to the action of the gravity. So that water, which this is the gravity water, which is drained due to the effect of the gravity. So it is the water in the large pores that moves downward freely under the influence of gravity. It drains out so fast that it is not available to the crops. The second one is the capillary water. It is the amount of water retained by the soil after gravitational water has drained out. So this is the amount of water that is retained by the soil after gravitational water has drained out. So this is, for example, here. Now the gravity water has drained out. This is the water which is retained by the soil. This is capillary water. It is the water in the small pores which moves because of capillary forces and is called capillary water. Capillary water is the major source of water available for the plants. And this capillary water, this is taken up by the roots of the plants, trees, and crops. So this is the source of water that is available for the plants. The third one is the hygroscopic water. So it is the soil moisture further reduced by evapotranspiration until no longer moves because of capillary forces. The remaining water, which is held on particle surfaces so tightly, is called hygroscopic water. Now you can see here, if I go back, we see this figure here. So now after the gravity water drains out, so you can see here the field capacity, which is the water content or the soil moisture that is held by the soil against the gravity. This will be taken up by the plants. So the plants, they will take up these water. You can see here that in hydroscopic water, what we have here is that this water becomes very tightly attached with the soil particles. So this water cannot be easily extracted by the plants. Now this is known as hygroscopic water. Soil moisture further reduced by the evapotranspiration until no longer moves because of gravity forces. The remaining water, which is held on particle surfaces so tightly, is called hygroscopic water. The water is held by adhesive forces and therefore it is unavailable to the plant. So it means that the capillary water is the major source of water available for the plants. You can see here the gravitational water. The soil is fully saturated, so the water will flow down due to the gravity. Now after the gravity water is drained out, so we have the capillary water, the water that is held by the soil against the force of gravity. Now this water, that is plant available water. This is the water that is taken up by the plants. And as the soil moisture will decrease because the water is used by the plants or the crops, so this moisture, it will reduce, and this will reduce to the hygroscopic water. This water will not be extracted easily by the plants for their growth. So it means that the water that is available to the plants, that is between the field capacity and between the permanent wilting point. You can see here that we have saturation, so much water, it drains out due to the gravity. So we have this as gravitational water because it drains out. So that's why this water is not available to the plants because it drains out fast. Now we have the field capacity. So water can be used by the plants. So this is the capillary water. Now the water, when it is used by the plant, so definitely the water content that will reduce, it will reduce to the permanent wilting point. Wilting point, wilt means that at that point where the crop or the plant is unable to extract further water, and then it tends to become weak, so it wilts up. This is what we mean by permanent wilting point. So little water, it cannot be used by plants, so that is known as hygroscopic water. And below this we have the oven dry, as you have studied in geotechnical engineering. So there is no water in the pores of the soil.
एक्सक्यूज मी
Now,
सर,
yes,
सर ये प्रीवियस स्लाइड में जो हमारे पास इस स्लाइड में सर जो ग्रेविटेशनल वाटर है सर, ये भी तो प्लांट्स के लिए अवेलेबल है सर.
this is available, but you see here that it drains out so fast. It drains out so fast that it is not available to the crops. You can see that when the rain happens, the water soil profile, it is wet, but you see that after some time it dries out. Now the plant, when it takes the water, the process is not that fast. That is very gradual process. You understand, when we supply the water to the crops, we do not supply every day. So you have to supply the water every 10 days, every 9 days, for example. So now the drainage is 2 days, 2 to 3 days, 2 to 5 days, let's say. So that water will not be available. What the plants will do for the rest of the period? So that is why this gravitational water drains out so fast that it is not available to the crops. When the crops take the water, the process is very slow. By the time it takes the water, this water is already drained out. Is the concept clear now?
ओके सर, ओके, अभी क्लियर है.
We will solve a problem, so you will further understand how we calculate this. That's why I bring so many of these pictures from different sources to let you understand. Now, in this case, you see the typical water extraction pattern in uniform soil profile. When the soil is uniform, so we have the root zone extraction depth. So this is divided into 4 zones, D by 4, D by 4, the first quarter, second quarter, third quarter, and the fourth quarter. So this is the general pattern, that the plants in the first quarter of the root zone extracts about 40% of the water for their evapotranspiration needs. Then in the second quarter, the plants take 30% of their evapotranspiration needs. 30% of the water that is taken from this second quarter. 20% is taken from the third quarter here, and 10% is taken from the fourth quarter. This is for uniform soil. It may slightly vary if we have non-uniform soil, and also this 40%, 30%, 20%, and 10% water which is taken up by the plants. So this can vary between comparative crops. If we have different crops, so there can be 10% variation between the comparative crops. But you will find this figure in the literature. So this is how the water extraction pattern you can see here. As we go down, then the extraction of water that is taken up by the plant roots to meet the evapotranspiration needs, it reduces. And that's why we talk about here the wilting point, that the water that can be taken up by the plants in this limit, the field capacity, and then the wilting point. Then below the wilting point we have water, but due to adhesive forces, due to that effect, it cannot be easily extracted by the plants. So if the soil moisture goes below the wilting point, then the water will not be able to taken up by the plants, and the plants will eventually wilt up, become weak, and eventually die. Next, we discuss a few terms. Readily available moisture. So it is that portion of the available moisture that is most easily extracted by plants and is approximately 75 to 80% of the available moisture. So that portion of the available moisture. Now what is the available moisture? We already talked about here that between this field capacity and the wilting point, this will be the available moisture to the plants. So it is that portion of the available moisture that is most easily extracted by plants and is approximately 75 to 80% of the available moisture, accounting for the other losses. Next, we have this permanent wilting point that we already talked about. It is the water content at which plants can no longer extract sufficient water from the soil for its growth and wilts up, become weak, and then if no water is available, eventually will die. Thus, the water available to plants is the difference of field capacity water and permanent wilting point water. So the water that is available to plants is thus the difference of field capacity and the permanent wilting point. So the permanent wilting point, that is, both are water contents. Clear? The permanent wilting point, it is that water content at which plants can no longer extract sufficient water from the soil for its growth. And at the field capacity, so it is the water that is held against the drainage. It means it is there, the water in the soil pores, and it is available to the plants. So this is known as available moisture, the difference between the two, or maximum storage capacity of soil. So again, you can see here we have this situation. So the water is drained by the gravity. After the drainage or this percolation, the water that is held against the gravity, so that is the field capacity. And at the permanent wilting point, you can see here that the water that is available to the crops, but at the field capacity, you can see the plants, they take up the water and used for the growth, but as the water will be used up by the crops, the moisture will decrease, so the moisture will drop to the extent that is this water, which is due to adhesive forces, stick to the soil particles and it cannot be easily extracted by the plant. So this is the permanent wilting point. So it means that during irrigation, we will now come to how to irrigate the crops, how we know to supply the water to the crops. So we will not allow the soil moisture to drop to the wilting point. So the moment the soil moisture drops from the field capacity to the level where still the plants can take the water, that is the optimum moisture content. That is the level that this soil moisture can deplete to that level and still it will not affect the crop yield. But below that, then the plants will not be able to extract the water for the growth and the crop yield will be affected. So this is the wilting point. This water cannot be easily extracted by the plants, and you can see that the crops, they wilt up and eventually will die if we do not have irrigation, artificial supply of the water to bring this soil moisture to the field capacity. So this is the important concept. From here, then we can determine that the quantity of water we need to supply and at how much intervals to the crops. We are gradually moving towards that concept. Now you can see here that we have the field capacity. This is the line which shows we have the soil water. Now this water is available to the crops that can be used by the crops for their growth, but this moisture content, it will drop because the water will be used by the crops. So it can reach to what is known as the wilting coefficient, that is the permanent wilting point. So below this point, the water is unavailable to the crops. The water is unavailable to the crops. So you can see that between the field capacity and the permanent wilting point, that is the water that is available to the crops. So we discussed the available moisture, the difference in water content of the soil between the field capacity and permanent wilting is known as available water or available moisture. So the difference between the field capacity and the permanent wilting point, that is known as available moisture, that is available to the crops. Soil moisture deficiency. Soil moisture deficiency or field moisture deficiency is the water required to bring the soil moisture content of the soil to its field capacity. What is soil moisture deficiency? It is the water required to bring the soil moisture content of the soil to its field capacity. Now next we discuss the depth of water stored in root zone. How we can calculate this? We have the moisture content. Now in this case, you see that this is the field capacity in terms of the moisture content of the soil. These will be expressed as percentages. We have the field capacity. So this is the field capacity moisture content. Then we have the wilting point moisture content. So you can see that this is the moisture content from here 0 to this level here. That is non-available moisture content or hygroscopic water. So between the wilting point and the field capacity, we have the available moisture content or the capillary water. Now you can see that the optimum moisture content, you can see that it is above the wilting point, because why it is called the optimum moisture content. You see that at the field capacity the water is available to the crops for their growth, and then the moisture content will drop. So it will drop and it can come to this wilting point. Now we do not have to allow it to fall down to the wilting point, because it will then affect the crop yield. So the limit to which the soil moisture or the water content is allowed to drop, to deplete, and still it will not affect the crop yield, that is known as the optimum moisture content. In order to estimate the depth of water stored in the root zone of soil containing water up to field capacity, so how we can calculate this depth of water? Let D is the depth of the root zone, FC is the field capacity, gamma D is the unit weight of the dry soil, and gamma W is the unit weight of water. Next we consider unit area, that is 1 square meter of the soil. So we defined this field capacity, weight of water retained in unit area of soil, divided by weight of soil of the unit area. So we can write down weight of water retained in unit area of soil divided by gamma D. So it is the weight of the soil of unit area. So gamma is weight by volume. So that's why this weight will be equal to gamma into this volume. Unit area multiplied by the depth. Now if I want to calculate weight of water retained, it will be the field capacity multiplied by this quantity. So weight of water retained in unit area, that will be equal to field capacity into gamma D into small d, which is the depth of root zone. Now depth of water stored, so that will be equal to FC gamma D into D divided by gamma W. So you can see here that these units will cancel out, and this will be the depth of water stored. You have field capacity multiplied by the depth of the root zone. This depth of water will be available for evapotranspiration. So available moisture depth, that is equal to gamma D into D divided by gamma W. So this will be equal to field capacity that we write down here minus the permanent wilting point. Because you can see here in this figure that the field capacity, it is this total distance here. This is the moisture content. But actually the depth that will be available to the in the root zone to the crops, that will be the field capacity minus the wilting point. That will be the available moisture content. So that's why this is actually the available moisture content. Now, estimation of depth and frequency of irrigation based on this soil moisture concept. So water is consumed by plants through roots. Significant moisture should be available in the root zone. Soil moisture in the root zone varies from field capacity moisture content to the wilting point moisture content. Soil moisture content is not allowed to deplete up to wilting point. The optimum level up to which the soil moisture is allowed to deplete is called the optimum moisture content. The irrigation water should be supplied as soon as the moisture falls up to the optimum level. So when the water falls to the optimum level, then we have to supply irrigation water to the crops. That is fixing the irrigation frequency. The quantity should be sufficient to bring the moisture to the field capacity, making allowance for application losses, thus fixing the water depth. Now you can see here that we have the soil moisture content. We have this field capacity, and we have this limit here. So this is the wilting point moisture content. Now the difference between the two, that is the available moisture content. Now in this available moisture content, we have already defined the readily available moisture content. It is that part which is that part of the available moisture content which is easily extracted by the crops for their growth, which is easily extracted by plant roots. Clear? Readily available moisture. This is what we define it here. Readily available moisture. It is that portion of available moisture that is most easily extracted by plants and is approximately 75 to 80% of the available moisture. So we can assume it that 75% or 80% of the available moisture. So this is the readily available moisture. Now you can see here that we have this optimum moisture content here up to this point. You see that the moment the moisture content drops to the optimum moisture content, we have to supply the water. We have to supply the irrigation water. You can see here. Now this we can determine that how much, after how many days we need to supply the water. This we can calculate. Again, the water is supplied to the crops, so the water will be used by the crops. As a result, the moisture content of the soil will decrease, and the moment it reaches the optimum moisture content, by this optimum moisture content we mean that the moisture content is allowed to deplete to the level that it is still extracted by the plants without any loss of the crop yield. So again, after this, you see that much time period, again we have to supply artificially the water to the crops to bring the moisture content to the field capacity. Again, it is used by the plants, and this will continue till for the entire growth period of the crops. So the depth of water in root zone, let's say DW we denote here. that will be equal to gamma D into D divided by gamma W, that will be equal to the field capacity minus the optimum moisture content, because this will be the readily available moisture. This is the moisture that is taken up by the plants easily, because if the moisture content goes below this optimum level, then it will start affect the crop yield. So it should not be allowed to reach to the wilting point, because at this point, at this soil moisture, then the plant will wilt up, become weak, and if no water is supplied, then eventually the plant will die. If Cu is the daily consumptive use rate, frequency of water can be calculated as this, that after how many days you need to supply the water. That will be equal to this depth divided by the consumptive use. So it will give us the number of days in which we have to supply the water, that after every 5 days, after every 10 days, we have to supply the water to bring the moisture content to the field capacity. So let us try to solve a problem to understand these concepts that we just discussed here. So you can see here that the problem is, after how many days will you supply water to soil in order to ensure sufficient irrigation of a given crop. So the field capacity of the soil, that is 27%. The permanent wilting point, that is given is 14%. A density of soil, so that is gamma D, 15 kilonewton per cubic meter. Effective depth of root zone, that is 75 centimeter. The daily consumptive use of water for the given crop, that is 11 millimeter. This is 11 millimeter per day. Now we assume that readily available moisture, that is 80% of available moisture. So how to solve this problem? Let us try to solve it step by step. So first we calculate available moisture. So we have this available moisture. That is equal to field capacity minus permanent wilting point. Minus permanent wilting point. So the field capacity, that is how much? 27%. So this is 27% minus the permanent wilting point, that is given as 14%. Now you see that these are the moisture contents, and how these values come, as you already studied in your geotechnical engineering, how you measure the soil moisture of the soil. The same concepts will apply here. Clear? But now here we are given these values in the problem, so we just want to calculate that after how many days we have to supply water to the soil in order to ensure sufficient irrigation for the given crop. So this will be equal to 13%. This is now the available moisture to the given crop. Next, we calculate the readily available moisture. So this readily available moisture, that is 80% of the available moisture. So we have this readily available moisture. So this will be equal to 0.8 into available moisture is now 13%. So 0.8 into 13%. So this is equal to 10.4%. Now next we have the optimum moisture content. So how we can calculate this optimum moisture content? This is here. The moisture content to which the soil moisture will be allowed to deplete and still it has no negative effect on the crop yield. So it will be simply this field capacity minus the readily available moisture. So the difference of these two, it will give us the optimum moisture content. So we have the optimum moisture content that will be equal to this field capacity, that will be equal to field capacity minus this readily available moisture. Readily available moisture. So this will be equal to 27 minus 10.4 . This is 16.6%. Now next, when irrigation water is applied, moisture is raised from this 16.6% to 27%. What we have to do is that now we get these limits here, 16.6% and we have this 27%. So this is 16.6% here. You see, this is what we calculated, 16.6%, and we have 27% here. This is 27%. So you see that when irrigation water is applied, moisture is raised from this 16.6% to 27%, to this 27%. When irrigation water is applied, so the moisture content will be raised from 16.6% to 27%. So it means that irrigation, when we artificially supply the water, So when we supply this water, so the moisture content, it is raised from 16.6% to the field capacity, which is 27%. Now, depth of water stored in a root zone. So, a depth of water that is stored in a root zone that will be equal to gamma d into d divided by gamma w, unit weight of water, into field capacity minus the optimum moisture content. So depth of water in the root zone, this is how we can calculate. This will be equal to, what is gamma d here, 15 kilonewton per cubic meter. So we have 15 here. What is d here, 75 centimeter. So divide by 100 to keep the units consistent. So we have 0.75. Unit weight of water, that is 9.81 kilonewton per cubic meter. We have this field capacity here, so it is in percentage. The field capacity, these are 27% here, so this will be equal to 0.27 minus the optimum moisture content. So this is 16.6 divided by 100, so this will be equal to 0.166. So if you calculate, this will be equal to 0.119 meter, or multiply by 100, so this will be equal to 11.9 centimeter. Clear? Now, depth of water available for evapotranspiration, that is 11.9 centimeter. This is the depth of water that is available for evapotranspiration. Now what we are given here, the daily consumptive use of water for the given crop, that is 11 millimeter per day. So the CU, that is the daily consumptive use for crop that is given to us, that is 11 millimeter per day, or it can be written as 1.1 centimeter per day. Now you can see, just to keep the units consistent here, 11.9 centimeter. So I write down 1.1 centimeter per day. Clear? Now frequency of water. Now we can calculate frequency of water. That is FW. So this is equal to a dW divided by Cu. What is a dW? This is actually dW. So this is how much? 11.9 centimeter. This is 11.9 centimeter divided by the consumptive use 1.1 centimeter per day. So you see the centimeter cancel out, day will go up, we get the number in days. So this is equal to 10.8 days. So FW that is, we can take it as 10 days. So it means that water should be supplied after every 10 days. This is the frequency of water. After every 10 days, the water should be supplied. Next, we discuss irrigation efficiency, some basic definitions. So efficiency is the ratio of water output to the water input and is expressed as percentage. Efficiency, the basic definition is the output divided by the input. So we defined here irrigation efficiencies. So it is the ratio of water output to the water input and is commonly expressed as percentage. The objective of efficiency concepts is to show when improvements can be made which will result in more efficient irrigation. The following are the various types of irrigation efficiencies. So we have the water conveyance efficiency, water application efficiency, water use efficiency, water storage efficiency, and water distribution efficiency.